Good afternoon again. So it's Paul again. Wanted just to thank everyone for joining today's webinar. Today we're going to cover the topic of GPU accelerated deep learning. As I mentioned, my name is Paul Floro and I'm a senior sales manager within the Fujitsu platforms business. Fujitsu are both a DGX and OEM partner with NVIDIA, and Fujitsu work very closely with NVIDIA to provide very unique business solutions and tailored infrastructure to both industry and government, and most importantly, we also do quite a bit in the space with education. Deep learning and machine learning is experiencing rapid growth, with customers learning to use GPU-enabled systems and tailoring algorithms to gain new insights, not only in their data, but to also find unique areas to help grow their respective businesses. So today's presentation will run for approximately around about an hour. Yesterday's presentation probably lasted, we got through the material in around about 45 minutes. So we'll allow some time at the end of the presentation for questions. And if you have any specific questions, you can type that question straight onto the actual question part of the portal. You'll see there that you can actually add some questions in there. So feel free to go and do that. If not, you can always ask your account manager, Fujitsu account manager, if you have any questions that you'd like to take offline. So without any further ado, I'd like to introduce Gabriel Noaje, who is the Senior Solutions Architect from NVIDIA, and he'll take you through the main presentation today. Thank you.
Thank you, Paul, for the introduction. Hello, everyone. Thank you for taking the time to join this webinar. Today, we're going to talk about the power of GPU accelerated deep learning. And in order to get a context for this, let's talk about the different terms that we normally use when we're talking about data science in general. We're talking about data analytics, machine learning, deep learning. So they're all interconnected. So data science is a broad field that covers everything related to data cleansing, preparation, and analysis. And it involves statistics, mathematics, programming, and creative problem solving to extract information and insights from the data. When GPU acceleration is used to improve the performance of data science workflows, we call this accelerated data science. Data analytics, machine learning, and deep learning are widely used approaches to solve problems in the field of data science. So let's go through each of them to understand what are the slight nuances between them. So data analytics has been around for a long time. It's nothing new. It's been used to examine data sets in order to draw conclusions about the information that they contain, using correlation, statistical modeling, and other methods. Machine learning uses statistics techniques to construct the model from the observed data. It generally relies on human-defined classifiers or feature extractor that can be as simple as a linear regression, or it can be something slightly more complicated. Things like, for example, spam filters. So this made possible things like spam filters. Deep learning, on the other hand, is a machine learning technique. So we consider deep learning as a subset of machine learning. It's a technique that automates the creation of these feature extractors, a process we call feature engineering, using large amounts of data to train complex deep neural networks. Deep neural networks are capable of achieving human-level accuracy for many tasks, but they require huge data sets and tremendous computational power to train. Several years ago, researchers started applying DNNs in a variety of areas, and they're reporting amazing results in a lot of areas, and we'll see a couple of them in the next slide. So let us dig deeper into the deep learning in the next few minutes. But first, let's take a look at how deep learning fits into the broader context of GPU accelerated data science with a couple of examples. So you can see here that many companies, organizations, or even governments are realizing that accelerated data science can help them be more effective or be more efficient. This is a partial list of industries and use cases where GPU accelerated data science can have a big impact. And I'm not going to go through each of these examples, but just to mention a few of them. For example, in healthcare, accelerated data science can be used to better predict diseases drivers with genomic medicine. It can improve healthcare health outcomes with analysis of electronic medical records. It can determine the best care or treatment for a wide range of health conditions, something that we are calling precision medicine. In energy and utilities companies, they're using accelerated data science to optimize energy distribution in smart grids, or reduce the outage, or do predictive maintenance. So there are many fields where this can apply. And I actually have a couple of more detailed examples at the end of my presentation on how this is actually being used in practice. So if the problem that you're working on is well-defined or straightforward enough that you don't need machine learning or deep learning, then there are more direct analytics methods like XGBoost, PageRank, similarity analysis that can still deliver good results with minimal effort. However, if you're working on this type of projects, I would highly recommend to check Rapid's open source platform. We do have a software solution that is accelerating many data science algorithms. If you need a more sophisticated approach, your data is organized into tables or sparsely populated data structure, and you know what the important features are, then machine learning techniques like regression, decision trees will generally work well. And lastly, if you have a big collection of data like images, videos, audio recordings, log files, or other dense data, and you don't know, or you don't have time to figure what the distinguishing characteristics of each class, then deep learning is likely a good approach for this. Often the best solution is actually a combination of multiple approaches with the output of one feeding into the next until you achieve the desired result. So as I said, we have tools that can accelerate each of these different type of tasks. So it turns out that deep learning is stunningly effective across many domains, and it's transforming the way computers achieve perceptual tasks such as computer vision, pattern detection, speech recognition, and behavior prediction. Some observers, including Bloomberg, have referred to it as the fourth industrial revolution. If you're in the research space, you might probably heard about Andrew Ng, who's a widely respected Stanford University professor and co-founder of the Google project. He believes that deep learning approach to AI is basically the new electricity. Many people want to know why and how deep learning is being adopted so rapidly. So there are basically three ingredients, or you may think that of them as the initial conditions that made the big bang of modern AI possible. The first was obviously the big data and the huge collection of examples from which computers can learn. Secondly, researchers like yourself that needed to develop parallel algorithms that allow data scientists to design and train deep neural networks to process the mountains of big data. And thirdly, was the introduction of programmable GPU accelerators that made possible for researchers to implement their algorithms on a flexible platform and to complete the massive amount of computation which is required in order to do deep learning, and you need to do this in a practical amount of time. So early researchers published their algorithms and neural network models in research papers or scientific journals, but they also released the software they created. As you might be aware, most of, if not all, the deep learning frameworks are open source, and the amount of research papers around deep learning exploded in recent years. So it can be helpful to think about deep learning as a way to map data samples from an input domain to an output domain. The input domain can be text data such as log files or financial data or images, or basically pretty much anything, any data that you have, whether it's audio, signals, video stream. The output domain is determined by the question you want to ask of the input data, and the question itself dictates the type of deep learning task that you would need to perform in order to map the output domain to the input domain, sorry, to the output domain. So the table that I have here, it shows a sampling of use cases where deep learning can be applied in healthcare, retail, or finance. So let's take one simple example. If the question requires a yes/no answer telling you whether something is present, then the task is obviously detection. If the question requires a more complex answer describing what types of things are in each output, then the task is classification. And if the question requires a shape or volume as an answer, the task is segmentation, and so on and so forth. So depending on the application, you might need to use a combination tasks to achieve a more sophisticated output. Let's take, for example, automatic language translation. You could use, for example, speech-to-text classification, followed by translation of the text into another language, and then again back to speech by using speech synthesis, which is another form of prediction. So all these are coming together, or all these are problems that you have to think about when you're starting your AI journey. So let's dig a little bit deeper to take a look how deep learning actually works in practice. So say you want to automatically identify various type of animals, which is a classification task. The first step is to assemble a collection of representative examples to use as a training data set, which will serve as the experience from which the deep neural network will learn. If you only need to classify, and again, this is a pretty common example, is the 101 of deep learning. If you want to classify cats and dogs, then you only need to have cat images and dog images as a training data set. You will need several thousand of images to make it conclusive, and each with a label indicated whether that specific image is a cat or a dog. You need to ensure that the data set is representative for all the pictures that you want to train. So it has to include a wide range of species, poses. The next thing that you need is the deep neural network model. And in this example, we start with a untrained neural network designed to perform a general task like detection. You can see that this is a very simple model of an untrained neural network. At the top of the model, there is a row or layer that has 4 input nodes, and at the bottom, there is a layer that has 2 output nodes. Between the input and the output layer, you have the few so-called hidden layers. In a real-life deep neural network, there are dozens, if not hundreds, of layers in between the top and the bottom layer. So just keep in mind that the design of the neural network model is what makes it suitable for a particular task. So there are better models for image classification, but there are completely different models for speech recognition, for example. So the goal is to train this deep neural network to distinguish between cats and dogs. So once you've assembled the training data set and you've selected the neural model, the next step is to choose a deep learning framework. And you have a multitude of choices, things like TensorFlow, PyTorch, MXNet, and you're using these deep learning frameworks to feed the training data set through the neural network. So for each image that is being processed to the neural network, each node in the output layer will report a number that indicates how confident the model is that the image is a dog and a cat. So once you're doing this entire process, you get what we're calling a trained model. So the trained model, once it's been trained on a representative data set, it will be able to distinguish between the different images that you might be throwing at it with a certain precision. Without going into the details, you can do further optimization on the training model, and then you'll go to the last phase of your application development, which is deployment of your model. So you will have a fully trained model, optimized, and you will be ready to integrate this into an application that whatever new data you feed, it will be able to detect dogs and cats. So this normally the entire development process for a deep learning application. Again, we're providing different software components for each of these tasks, and I'm going to talk about them in the next couple of minutes. So first, what are the challenges that you might see when you're trying to adopt deep learning? The first is that this is still relatively a new computing model, and most data scientists, developers, and researchers don't necessarily have a lot of experience working with it yet. And to apply deep learning effectively, you need to learn how to approach problems a little bit differently from from a more data-centric perspective. The other challenge is the algorithms used for deep learning, which continue to evolve and improve very rapidly. So as I said, especially in the research space, there are papers, dozens of papers that are being published almost daily. And the final challenge is that you have to have a platform that provides you the capability and the computational power to do all that. So let's take a look at some of the things that NVIDIA is doing to help you overcome these challenges. And in order to understand why NVIDIA and why GPU computing, you have to understand that the GPU itself provides a tremendous computational power. And if you're comparing that with the CPU, and you have on the right-hand side a graph, which is showing the performance of CPUs over time, and you might recognize this as we call this curve Moore's law. We're seeing that the Moore's law and basically the performance of the CPUs are actually starting to plateau in recent years. However, the performance of GPUs, it's on a continuous ascending trend, and the gap in between the performance of a CPU and the performance of a GPU only continues to increase. And I'm not talking just, or this difference in performance is not just coming from the hardware itself. We're working on NVIDIA is working on the entire software stack, from the programming language to the libraries, algorithms, and applications. So what are the considerations when you're building an AI platform? Obviously, the first and the most important is developer productivity. Especially as a researcher, you want to get started as soon as possible to work on your new discoveries and on your new problems that you're interested in tackling. Obviously, you can start small. You can run initially on one single GPU or on a workstation, but you'll soon find out that you're hitting limitations, and you want to scale your work, and scaling has to come with its own performance, and there are challenges when you're trying to scale deep learning. And obviously, last but not least, the budget is important, so the total cost of ownership. This is mostly on the AI platform from a hardware perspective mostly, but there are a lot of challenges from the software perspective. So currently, GPU accelerated computing is helping to solve this complex problem, and choosing the best software framework is not necessarily an easy feat. It requires a high level of expertise. You need to manage multiple components like drivers, libraries, framework dependencies. So the true TCO for an AI platform, it actually boils down to this. From the day you're actually deciding that you want to embark in the journey of deep learning, which is your day one, it can take up to 3 months or more until you actually get insights from the data, because there are multiple steps there that you need to take care of. And it's not something easy, or just when you're looking at deploying an AI infrastructure, it's not just looking at the spec sheet and you're just choosing whatever you think provides the best performance. There are multiple components that have to go into your evaluation criteria, like the hardware architecture, the operating system image, the AI software stack, and the expertise and the innovation, basically the support that is being provided. And especially as a researcher, you might not even be interested in having to look at all this. You want something that you can deploy and it just works. So NVIDIA came up with what we are calling purpose-built AI supercomputers. This is an entire range of products called the DGX family. We have right now 3 products under this family, starting with the smallest, which is a DGX station that goes under your desk. It's whisper quiet, it's water cooled, and you can deploy it in any type of office environment. And it contains 4 GPUs in it. The next one, or the next 2 other products are server grade. They need to be deployed in a data center, and they're DGX1, which has 8 GPUs inside, and the DGX2, which has 16 up to 16 GPUs inside. On top of this, these are delivered as what we're calling appliances. On top of them, we have the DGX software stack, and I'm going to talk a little bit later about the things that we're putting together inside of the DGX software stack. But any of these 3 products, they come as I said, as an appliance that you can get it and get started with it immediately to get your work done. So from a hardware perspective, at the very core of all these 3 products, you have the NVIDIA Tensor Core GPU. And this is specifically built for AI. And one of the features, it's called the Tensor Core. It's a hardware feature inside of the GPU that is providing optimizations for specific operations that are the foundation of deep learning. For those of you more technically inclined, those are matrix multiplication that are being done in a one single instruction cycle. On the other hand, we're doing optimization on top of the hardware itself. As I said, we're doing optimization in the CUDA programming language, which helps you program the GPUs. We are doing optimization at the library level, things like cuDNN, which are optimized to take benefit of the hardware, like the tensor cores and other things inside of the NVIDIA GPU chip. And obviously, we're working with all major frameworks. There's no one single framework, deep learning framework right now that is not GPU accelerated. So a broader view of the software platform. It's here again. I'm not going to go into all the details, but suffices to say that NVIDIA is optimizing at all the different levels, and we're looking holistically at both of the training and the inferencing portion of deep learning. In order to make the adoption easy, adoption easy, we came up with a common software stack across the DGX family in order to enhance the productivity. This is called NVIDIA GPU Cloud, or NGC in short. And NGC provides a single unified stack for deep learning frameworks. It works across the entire DGX family. It provides predictable execution across the platform. And at the core of NGC, you have the DGX containers, which enable for easier experimentation and provides easy deployment methods. So if you look, take a deeper look at what NGC is, you will see that the foundation is are the Docker containers. So there are a couple of dozens of them right now, and we're not only addressing the deep learning space, but we have containers for machine learning and even high performance computing. On top of that, we are providing under NGC model training scripts for NLP, image classifications. We have pre-trained models. We have even entire industry workflows for specific fields like medical imaging, intelligent video analytics, and a couple of other things like Helm charts, Kubernetes integration. So all these are coming together to basically save you hundreds of thousands on software engineering. And we are making sure that we optimize the frameworks. Our engineers are spending hours and days to make sure that these containers, once they hit NGC, they're optimized. So we have monthly framework releases, and we ensure that you get the maximum performance for the DLI. This is just to reinforce that message. If you're looking, these are a couple of containers that I picked from the NGC, and if you look at the performance in between different releases, you will see that the performance, it's only going up. So overall, what the impact of the DGX system on your adoption timeline is definitely shortened. So instead of spending, as I said, with the DIY solution up to 3 months in order to get it up and running, you're reducing this. If you're deploying a DGX solution, you're reducing that to as short as 1 week. In the case of, let's say, more complex solutions, sometimes if you're having just a DGX station, you can be up and running in a matter of hours. So you're just plugging the appliance, downloading the container that you need, and you're ready to go. But as I said, having one workstation or one server is the beginning of your journey. Soon you'll find out that you want to expand beyond that, and the size of the models is increasing steadily. New models that with new requirements are being introduced. So you will have to scale your deep learning computation. So in order to do that, NVIDIA has put together what we're calling the DGX SuperPod, which is basically an AI supercomputer. We've deployed this in our data center, and we had it running for multiple months now. It's actually ranked the 20th most performant supercomputer in the world. And this DGX SuperPod, it provides an instant AI infrastructure. You can actually purchase exactly the spec for the SuperPod. We are providing the white paper for this SuperPod with all the details from the server configuration, networking interconnect, storage, and all the details in between. We've been doing this for a while now, and we've shown proven performance of this solution. You might have heard about MLPerf. MLPerf is a community benchmark that has been put together by Google, Facebook, and other major players in the deep learning space. And NVIDIA has been winning all the categories for which we submitted results. And you can see here a couple of details on this benchmark. But one thing that I want to draw your attention upon is that not only we are providing the best performance at the chip level, at the server level, and at scale, but we actually improve. So up to now, there have been 2 versions of MLPerf, and we've been improving over our own performance. And this is due to the innovation that we are doing in the software. So the hardware remained the same in between the 2 submissions, but the increase in performance that you're seeing, it's only due to the performance improvement that we're doing on the software stack. So we've distilled our experience in what we are calling reference architectures. We're working together with our storage partners to provide white papers. So these are available on the NVIDIA webpage. This reference architecture, basically, they provide a simplified, validated infrastructure that has been tested. If you're downloading any of the white papers, you will see that benchmarks are being made available, and you don't have to go through the entire process of figuring out how you can put all this together. Now, from a data center perspective, there are also big reduction in costs, so the total TCO goes down. And this shows a comparison between a traditional hyperscale cluster. So in this case, we're having 300 dual CPU servers, CPU-only servers, that costs roughly $3 million and consumes something around 180 kilowatts. In order to achieve the same throughput, you could simply deploy one single DGX. So the throughput that you get out of one DGX2, it's equivalent to the throughput that you get from 300 dual CPU servers. But obviously, there are big savings in cost, space, and power. And if you're in the data center, if you're a data center admin or interested in these details, there's obviously big interest to move to a GPU accelerated solution. But again, hardware, it's not everything. We are providing a DGX pod management software. It's a suite that we're calling DPOps. It's a collection of open source tools that we've put together. Again, our engineers are working to make this management software as easy as possible to be deployed and managed. So this brings together things like Kubernetes, Slurm, things for management, and like Prometheus or Grafana for visualization of what's happening inside of the cluster. So overall, we're the fact that you're deploying an NVIDIA DGX solution, we are basically getting an end-to-end AI expertise. And that is the NVIDIA expertise from the chip level all the way to the big scale out systems. Now, let's go through 3 examples that I put together here that are showing real DGX customer stories. The first one is it comes from medical space. So this regarding retinopathy of prematurity, or ROAP. that affects the youngest, smallest, and most vulnerable infants. So doctors can treat ROAP if they can catch it early enough, but there's no objective way to determine which cases need treatment. So researchers at the Atinula Martinez Center for Biomedical Imaging at Mass General and Brigham and Women Hospital in Boston, they used a DGX-1 with CUDNN accelerated frameworks to develop an algorithm that could automatically determine the severity of ROAP disease. So they use a data set of more than 6,000 images matched with expert diagnosis in order to train the deep neural network to differentiate the different orders of severity. Another example, again, is coming from the healthcare space. This is the Geisinger, which has amassed a huge collection of digital records and medical images for nearly 2 million patients. And they're using, based on this multimodal data sets, they're using both DGX1s and DGX2s as a foundation for AI projects. And using, for example, clinical radiology informatics with deep learning, they can early and accurately diagnose intracranial hemorrhage, which is critical for patient outcome. Even closer to our region, we are doing a similar work with SNAC in Australia. Another example now from the astronomy space, and again, I know this is very topical for Australia. This is an example of deep learning usage for the extremely large telescope, which is going to be completed in 2024, and it's going to be one of the largest telescopes that was ever built. Scientists at Université Paris Diderot and Observatoire de Paris, they're using a DGX-1 to revolutionize adaptive optics. So they're using deep learning techniques to image correction on distorted images, things that otherwise would impede their work. So these are only a couple of brief examples on how DGX hardware and DGX solutions are being used by researchers. I highly encourage you to tune in on the NVIDIA website on 14th of May. Our CEO, Jensen Huang, will deliver the keynote for our GPU technology conference for this year, and we're going to have some great announcements. Some of them are actually related to the DGX and deep learning frameworks. So I highly encourage you to tune in on 14th of May on the NVIDIA website, and that is 11 p.m. Australian Eastern Standard Time. Obviously, the keynote will be recorded, so you'll be able to watch it later if you want. So you're ready to get started. The first steps to get started is always to get clarity on exactly what the problem that you need to solve. If you decide to apply deep learning, you'll need to determine which AI tasks are involved. So it could be detection, classification, or a sequence of several tasks that implement a more complex workflow. And last but not least, you have to decide which platform you want to train and which platform you want to deploy. So if you're ready to get started, as I said, the DGX appliance is one of the best solutions available, and Fujitsu is one of our NPN partners. And Paul will give you a couple more details on how Fujitsu can help you start the deep learning journey. So with that, thank you for listening, and I'll pass this to Paul. Thank you.
Thanks, Gabriel. Look, I really appreciate your attention, and I just got a couple of more slides that I wanted to run through. The first of which is, if we can move to the next one, associated with where does Fujitsu play in this? So not only are we a NGX partner, but we can offer a comprehensive range of varying different solutions covering the full DGX portfolio. That's from the DGX pod, which is encapsulated with the appropriate storage and appropriate network. Over on top of that, of course, you're going to need to have the right data center cooling and power requirements in order to be able to drive the performance that you need within the data center environment. Then, of course, we have the standalone servers being the DGX1 and the DGX2s. DGX stations for any of the researchers that are looking to start to do some algorithm work and train algorithms. And of course, there's also edge devices that we can also provide. So there's edge devices like Xavier, which is the NVIDIA Xavier product, which we're starting to see a lot of prevalence, especially when it comes to utilities and augmented reality type environments. Fujitsu can also provide OEM products. That's effectively products that use the NVIDIA GPUs in servers, like our own Fujitsu servers, HPE and Lenovo servers, which we can provide. And of course, as I mentioned previously, looking at the network using high performance InfiniBand or Ethernet networks from vendors such as Mellanox, accelerated flash and object storage offerings from vendors such as NetApp and HPE. And of course, again, the right data center requirements and racking and cooling solutions. Fujitsu can also provide, especially into universities and research, demo units. If you want to get started, you want to see whether that's the right product and the right solution, be able to find ways that you can then customize the solution you want to end up with based on what grant money you might have. And more importantly for us, it's how we build relationships with the university researchers, utilize the experience and areas of expertise that you would have, and build collaboration with our industry and government customers. Such collaborations can also inject good funds and strong funds into further exploration of your areas of research that are aligned to what industries are requiring. So Fujitsu are keen to work with you in order to do any workshops, do some architectural work, get NVIDIA in with us in order to tailor appropriate solutions to meet your deep learning and AI business requirements. Moving forward then, Fujitsu can also offer leasing options. Now, I know when it comes to education, you typically get grant money and you look to be able to exhaust the requirements that you have for those specific grants. But where you may not have the upfront cash flow, please remember that Fujitsu can also offer leasing options. And as long as the lease terms are from 24 to 60 months, as far as a commitment, minimum transactions need to start at around about $60,000. And of course, they're subject to credit approval and lease documentation. So if there are any further questions, I don't want to go and continue on the leasing side. However, that is an option if you want to explore that. We're happy to have those conversations with you. If there are any questions, I noted that there were a couple of questions that were asked. If there's anything specific that you would like to know, anything that we can specifically help you with, Fujitsu and the NVIDIA team are very keen to help you. So please reach out to either your Fujitsu account manager or to any one of us that are on this call, and we're more than happy to help you with anything that you might need in this area. Really appreciate you spending the time with us this afternoon. And now I'll open up the floor if there are any specific questions or anything that we'd like to discuss further. So I'll open up the floor.
Okay, thank you, Joel. I'm seeing two questions, so I'll pick those two first and then give others time to ask further questions. Please use the chat window to send more questions if you have. So the first question is the number of hidden layers the differentiating factor between machine learning and deep learning? Actually, no. So the the layers and the deep neural network is actually the characteristic of deep learning. In machine learning, you don't have or you're not using a deep neural network model. So the deep neural networks are the characteristic for deep learning. However, the number of hidden layers have impact on the accuracy. It has an impact on the performance of the model. It has impact on the other characteristics of the model itself. The number of hidden layers actually means the number of parameters that you have to tune during the training process. So the bigger the model, the more complex and the more computationally intensive to train that that model. Okay, the next question is, are there any upcoming Clara platform trainings available? Actually, we are just finishing a series for the APAC region around the Clara platform. So earlier today we had the fourth installment of this training session. They are recorded, so if you're interested, please drop your email in the chat window. If you're interested, then my colleagues from Fujitsu will get your details, and we can send you the information. The sessions have been recorded. There are 5 sessions in total, only related to Clara. There are multiple components inside Clara, from Clara Train to Clara Deploy, and Clara Genomics. And during this webinar series, we are talking about those different components. So definitely we have lots of resources available regarding the Clara platform. Okay, any other questions?
If there are no other questions, it's Paul again. I just wanted to again thank you for your attention and for joining us today, this afternoon on this webinar. I wanted to reiterate the fact that Fujitsu is obviously a very strong partner with NVIDIA, but has been in the high performance computing space, as you may be aware, obviously working hand in hand with NCI and having delivered the most recent iteration of their supercomputer, Gaudi, which should be, with most of it is online, but as part of that system, we have 640 NVIDIA V100 GPUs in that cluster. So there's going to be additional resources available for you guys to be able to go and utilize and do some of the deep learning workloads that you may be desiring to work on. We're here to help you. So if there's anything at all that anyone from Fujitsu or NVIDIA can do to assist, we'd like to hear from you, and we're more than happy to work with you in order to not only help you with your research, but to find ways that we can tie your research back into industry for the betterment of all of us. Thanks again for all your time, and we look forward to hearing from you soon. Thank you.